Okay, in this part of the lecture, we're going to discuss section 11.2, which is going to be periodic motion. Periodic motion is going to be the motion that repeats itself in a definite cycle. So periodic motion occurs when an object has a stable equilibrium position and is subject to a restoring force that acts when the object is displaced from equilibrium. When the restoring force is directly proportional to the displacement, such as what you see with Hooke's law, f of x is equal to minus kx, which is often the case for small displacements, then the resulting motion is called simple harmonic motion. So let's take a look at this particular figure here where we've got this metal glide that has air that's coming out through these little holes here. That's an attempt to push this actually away from the surface, but still have it be a guide that this object can move along. It's also tied to a spring. That spring is going to have this object centered at some particular position. We're going to call that 0. And we're also going to call this length here the x-axis. So this object, once we set the spring in motion, whether we bring it back or whether we stretch it out, that spring is going to want to act in the opposite direction. So it's going to want to either pull this back or push it forward. If there are no other forces acting on it, which is what the air through the holes there tries to do, tries to prevent friction from acting on it, then what's going to happen is that with that force given, that's going to be the only force acting on this particular object. And it is going to oscillate between some distance a away from the equilibrium and then some distance minus a on the other side. So it's going to go through those extreme amplitudes and it's going to work its way back and forth and back and forth. While it is here, the forces that are going to be acting on it is just the normal force of gravity, or the normal force, as well as gravity. Over here, you're going to have those two forces as well, but the spring is going to try to push it. It's going to try to push it this way, and therefore you're going to get some acceleration this way. Over here, you can see where it's gone out to its limit, and the spring is going to try to bring it back, and so it's going to accelerate it this way. I have to click on this particular link because when I tried to click on the section 11.2 link there, it put me in section 11.1. So that's why I'm doing it this way. Okay. So we've already discussed periodic motion or oscillations. And we've already discussed the obeyance of Hooke's law in something like this. So we've already talked about the frictionless horizontal air track, which this thing is on. And so we've already given a pretty good description there as far as what's going on. We now know that if we take the force in the x direction, which is going to be the mass times the acceleration, and solve that for a, then it would be the acceleration is going to be proportional to the force acting in the x direction divided by the mass. The mass is going to want to keep it from accelerating. So we've had the free body diagram show us what's going on when x is negative, when x is 0, and when x is positive. We knew that when x is negative, that the force and the acceleration were headed in the positive direction because the string's trying to push it out this way. When x is 0, there was no net force of the spring, it was at rest. When x was positive, the spring was going to try to pull it back, so the acceleration was going to be in the negative x direction. So when x was less than 0, you can see here that the glider is displaced to the left of the origin. You can also see that the spring here is compressed. Since the force here from the spring is trying to push it this way, f of x is going to be greater than 0, and therefore the acceleration is going to be greater than 0. That's why the free body diagram at that point looks the way it does. Here at x is equal to 0, the spring is neither stretched nor compressed, therefore it exerts no force. And so all you have is a normal force and the gravity force, which are balanced. When x is greater than 0, then that means this spring is stretched, and now it is trying to pull this object back in this direction. So that means that the force in the x direction is less than 0, and that means the acceleration in the x direction is less than 0. So on either side of the equilibrium, f of x and x always have opposite signs because of the way the x direction is defined and the action of the force. The force is always trying to oppose its displacement. The spring force earlier was introduced as k times the change in L. If we turn around and we replace the change in L by minus x, we end up getting our Hooke's law formation of the force, which we've come to know and in some cases may hate. The units are going to be newtons. And you can see the discussion regarding the negative signs when x is greater than 0 or when it's less than 0. The acceleration is not constant. So it says here, don't even think of using the constant acceleration equations from chapter 2. Figure 11.15 shows a complete cycle of what's going on. We'll get to that in a minute. If we displace the object to the right at a distance a and release it, then its initial acceleration is going to be in the opposite direction. So it's going to be this way. As it approaches the equilibrium position, the acceleration decreases in magnitude, but its speed increases. It overshoots the equilibrium position and then comes to a stop on the other side. Comes to a stop at x is equal to minus a. Accelerates back to the right, overshoots again, then comes to a stop here, and then goes boing, 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 boing all the time. If there's no friction to reduce that spring force, it's going to continue to do that forever. So we can see here, we've got our glider guide. We've got our positions of x is equal to a, x is equal to 0, x is equal to minus a. If x is equal to a, acceleration pulls back this way. The velocity is initially 0. Then as the acceleration dies off, the velocity will increase. It's just, it may actually be larger in magnitude than the acceleration. As you get here towards 0, then the velocity is going to be headed in this direction, which if you look at it with magnitude and direction is going to be at its maximum here, but in the minus direction. The acceleration here is 0 because there's no net force at that point. As you go through here, the acceleration begins to want to start to push the object this way. However, there's enough velocity for it to continue to move in this direction. It does that until it gets all the way down here to minus a. When the velocity finally gets to 0, but the force is trying to accelerate the glider back the other direction. Then you can see here the velocity starts to pick up, but the acceleration decreases. When it gets back to equilibrium, there is no net force, but the velocity is at its maximum and it's pointed in the positive x direction. Here, the velocity begins to slow down. The acceleration in the opposite direction is picking up. And then when we get back to this position again, we have the same situation that we had up here. So the motion that's just described, a periodic motion under the action of a restoring force that is directly proportional to the displacement of the equilibrium, is called simple harmonic motion, SHM. Many periodic motions, such as the vibration of quartz crystal in a watch, vibrations of molecules, motion of a tuning fork, and the electric current, are approximately simple harmonic motion. But not every periodic motion is simple harmonic. The amplitude of the motion is going to be denoted by A, and that's going to be the maximum magnitude of the displacement from equilibrium. In other words, it's going to be the maximum value of x. The amplitude is always going to be positive, while the x direction may be positive or negative. When we talk about the amplitude, we're talking about the greatest separation that this has from its equilibrium position. That separation is going to be marked as A. The total range of motion is going to be twice that. A cycle is going to be one complete round trip. In other words, from A to minus A and then back to A. Another way to look at it is from A to 0, then to minus A, then back to 0, and then back to A. The period is going to be the time for one entire cycle. It's always going to be positive. In the SI unit is the second, but sometimes is seconds per cycle. The frequency is the number of cycles in a unit time, and it's always going to be positive. So the SI unit is going to be the hertz, or cycles per second. It's going to be the reciprocal of this. The angular frequency is going to be 2 pi times the frequency. So it's going to be the angular frequency is 2 pi f. And we're going to learn later why that's a useful quantity. It represents the change of an angular quantity, not necessarily related to rotational motion, that is always measured in radians. So it's going to be radians per second. So again, the frequency is going to be 1 over the period, or the period is 1 over the frequency. And your angular frequency is going to be 2 pi times the frequency, or 2 pi over the period. So the key thing here is only in simple harmonic motion is the restoring force directly proportional to its displacement. In more complex types of periodic motion, the force may depend on its displacement in a more complicated way. However, many periodic motions are approximately simply harmonic if the amplitude is small enough that the force is approximately proportional to the displacement. So that's the important point that we want to drive home here. Again, there are some more exercises here I would encourage you to go through and to observe.